Okay, I think we should start. Good morning, everyone. Thank you for joining us. I'm Mary Salvaña, Assistant Professor in the Department of Statistics at the University of Connecticut. On behalf of the organizing team, I'm pleased to welcome all of you to the Spatio-Temporal Statistics and Data Science online seminar series. This series brings together professors, researchers, practitioners, and students worldwide to explore methods, theory, and applications of space-time data. Our goal is to provide a platform to share ideas and to spark conversations that push the field forward. We're grateful for the support of the ASA section on Statistics and the Environment, or ENVR, the Royal Statistical Society's Environmental Statistics section, and the International Environmetric Society, or TICE, whose communities help broaden the reach and impact of this series. Each seminar runs for 60 minutes. The speaker will present for 45 minutes, followed by 15 minutes for questions. Please feel free to type your questions into the chat at any time. We'll collect them and raise them after the presentation. All talks are recorded, and the recordings, along with the slides, will be posted on our website. We host one seminar each month, and you're also welcome to nominate future speakers. To stay updated on upcoming events, you can subscribe to our mailing list, and you'll find those details as well as other resources at stsds.org. With that, I'll turn it over to my fellow organizer, Jordan Richards, to introduce today's speaker.
Nice, thank you very much. Hello everyone, I'm Jordan Richards. I am a lecturer in statistics at the University of Edinburgh in the UK, and I have the pleasure of chairing today's talk. So it's my pleasure to introduce Mary Salvaña. Mary is an assistant professor at the University of Connecticut in the Department of Statistics. Before joining UConn, she was a postdoctoral fellow in the Department of Mathematics at the University of Houston, and she earned her PhD in statistics from the King Abdullah University of Science and Technology, KAUST in Saudi Arabia. Her research focuses on spatial and spatio-temporal statistics, computational statistics, high-performance computing, and the study of extreme and catastrophic events, risks, and disasters. With that, I'm happy to turn it over to Mary to begin today's talk. The floor is yours.
Thank you, Jordan. I'm excited to present to you this work on multi and mixed precision computations for spatial and spatio-temporal statistics. This is a joint work with my colleagues at the King Abdullah University of Science and Technology, Saudi Arabia, Bright Skies in Egypt, and Pusan National University in South Korea. So most of us have had to work with a very large covariance matrix or a positive definite matrix, and we needed to get the Cholesky of that matrix. What it would look like computing that in R is that we have this 20,000 by 20,000 matrix M, and we would call the function Chol, and we wait. It will take the cross product will take about 1 hour. The Cholesky will take about 20 minutes, and you will have to wait 1.4 hours. And that takes about 3 gigabytes in memory. And this is just for one Cholesky factorization. In practice, of course, we need to repeat this many, many times for likelihood evaluation, MCMC, and also cross-validation. So the cost can quickly become very prohibitive. On the right, I do the same computation using this R package MPCR, and I just change the precision of the big covariance matrix. I try first with the same precision as the base R, but now it's MPCR double, and I just have to wait for 24 seconds. Same amount of memory, 3 gigabytes. And here, I also tried the single precision. I saved the matrix A as a single precision matrix, then did a cross product and Cholesky, and I cut down my computation time in half. And in the end, I used only 0.04 gigabytes of memory. This illustrates how precision can be used to overcome some of the computational problems that we have in our work. To understand how this is possible, we need to review concepts on floating point arithmetic. So 1980 was a historic year in the world of computing. That was when Intel released the 8087 math coprocessor chip. At the time, computers were not be able to handle floating point numbers and computations directly, so this separate chip was designed to carry out those operations. It marked the beginning of dedicated hardware support for floating point arithmetic. So what are floating point numbers? Floating point numbers provide a way for computers to represent or approximate real numbers. They are what we input to the computer, and that's also what is given back to us after we do our computations. Unfortunately, there is no way to encode the wide range of real numbers on a computer, and so the best way we can do this is by approximating them. This is the anatomy of a floating point number. Let's say we have x. Here, S controls the sign of the number. It's 0 if it's positive and 1 if it's negative. M is what we call the significand or mantissa, which holds the fractional part of the real number. Beta is the base. It's 2 for binary computers and 10 for decimals. E is the exponent. It tells us the position of the decimal point or the binary point. And T is the precision. It tells us the approximation error due to rounding. This is what it would look like to represent 12.34. In the binary system, in the decimal system, beta is 10 and it's positive, so S is 0. If you remember how to write scientific notations, M is going to be 1.234. The whole exponent is E minus T plus 1. It's 1. And when you go back to its original form, it's exactly 12.34. If we want to try binary, you can Google how to convert a decimal to binary. You will see that M is going to be 1.10001010011. E minus T plus 1 is 3. And once you convert it back to decimal, it's not exactly 12.34. It's 12.3359375. There's also another significand you can use, the longer one. If you want to include more zeros and ones, you have the third row, and if you convert it back to decimal, you will get close to 12.34. So we can see that depending on what representation you choose, there is some accuracy lost when you shorten the significand. When we do a lot of numerical computing, this is an issue that is good to be aware of because these approximation errors might compound. We might not think about this because we simply use whatever software we like, R and Python. And however R or Python likes to save our numbers or matrices, we don't really investigate it as long as the results we get look acceptable to us and realistic based on the problem that we are solving. But it turns out, as I will elaborate in this talk, that shaving off some accuracy can speed up your computations. So if you're actually comfortable with this representation of 12.34 and the end result of your computation or solution does not change that much, then you will actually enjoy some speed up in your computations. Before we proceed, let's review the difference between accuracy and precision. They sound similar, but they're referring to two different things. Accuracy refers to how close a number is to a known true value. Precision on the other hand, refers to the number of significant digits or bits in a floating point number. You can think of precision as how many numbers can you find between two numbers? So real numbers have infinite precision, and floating point numbers, they have finite precision. Because of their design, you can count the number of floating point numbers between any two floating point numbers. The number of bits used to store a number will often cause some loss of accuracy, just like what we saw in the previous slide. Since computer memory is limited, we cannot store numbers however many bits we want. At some point, we have to cut off some digits or bits. But how do we cut off? The IEEE standard 754 will tell us how. Most numerical computing today is done in this standard. It governs the standards for floating point formats and arithmetic. It lays out the rules on how numbers should be stored in the computer. There are three most commonly used precisions in the IEEE standard 754. We have the half precision, which is also called the 16-bit format. This is equivalent to 4 decimal places, which is about 2 bytes of memory. Another one is the single precision, or 32-bit format. This is equivalent to 8 decimal places and 4 bytes of memory. The last is the double precision, the most commonly used format. It's also called the 64-bit format, and it's equivalent to 16 decimal places, 8 bytes of memory. In this figure, we see how many bits we allocate for each portion of the floating point number. We allocate 1 bit for the sign, so it's just 0 or 1. Then depending on the precision that you choose, you will have different number of bits for the exponent and the significand. Double precision offers the highest precision among these options, and it's very ideal for applications that require a very high level of accuracy, and it consumes the most memory among these three. The second, this single precision is becoming more popular. It trades some loss of accuracy for more speed. The half precision is actually the industry standard for AI machine learning models. If you're comfortable for trading more loss in accuracy for more speed, then half precision is an option. Half precision is twice as fast as single precision and 4 to 8 times faster than double precision. Here we see an example of how precision impacts performance in practice. We have here the number of images that you can process per second. If you switch from FP32 or single precision to half precision, FP16, you double the number of images you can process. We see the same improvement in matrix-matrix multiplication. You can 12x the number of operations per second if you use half precision over double precision. Just to illustrate what's happening with these precisions, this is how your pi would be stored. In half precision, you have 3.141, single, it's 3.1415926, double, which is the default in most softwares, you have 16 decimal digits. You can go higher than double, you have quadruple and octuple. So if you don't really need all these decimals, then maybe you should explore half and single precisions. Physically, this is how pi is going to be stored in your computer's memory. As you can see, half precision is very lightweight. It does not take up that much space, unlike double precision that takes up a lot of memory. The IEEE standard 754 has a very rich history. It has changed the world of computing. It has created a homogeneous world of computing that we enjoy today. Before, each computer had their own floating point number system, and some were binary, some were decimal, and even among binary computers, they would use different bases, base 2, base 8, base 16, and everybody had a different precision. So when you do a computation in one computer or processor, and you do the same computation in another processor, you will get different answers. The lead architect of the IEEE standard 754 is Professor William Kahan. He is known as the father of the floating point standard. Because of this work, he won the 1989 ACM Turing Award. So the standard was first published in 1985, where the single precision and double precision they were defined. The next major revision was in 2008, where half precision and quadruple precision were introduced. And the last revision was in 2019 for just some minor enhancements. So choosing precision, it's not just a matter of personal preference. You have to check the software that you are using, whether they are able to support your choice. Double precision, you don't have to think much about it because it's what's given to you by default. It's available when you call the double type, that's what you get. In TensorFlow, it's tf.float64. In PyTorch, torch.double. It's a default numeric class in R. Single precision, it's getting more available in most C, C++ systems. It's what you get with the float type. In TensorFlow, it's tf.float32, and in PyTorch, it's torch.float. To use it in R, you need to use special packages like float and MPCR. Half precision is not that widely supported, but you can use it if you have some special libraries. In TensorFlow, it's tf.float16, and in PyTorch, it's torch.half. To use it in R, you have no choice but to use our R package MPCR. Aside from software, you need to think about the hardware that you have. For double precision, as long as you have a computer, it's there. Single precision, a new generation of computers, CPUs, GPUs have single precision. Half precision, not that well supported, but it's available in Intel Xeon CPUs and in most modern GPUs, cloud, and supercomputers. Over the years, we have seen a rise of low precision computing. The state of the art right now is larger models and high performance computing, and shaving off some precision is one way to increase speed. A lot of the push for low precision computing comes from the goal of making AI and machine learning systems more scalable. The models are bigger and they are looking for more efficient ways to train them. And so in response to this demand from the AI and machine learning communities, hardware vendors or chip makers have been designing chips that support low precision computations. So we have here Google's Tensor Processing Unit, NVIDIA's GPU, and Intel's Neural Network Processor. Chip makers have been trying to push the boundary on how low we can go in precision while keeping the results accurate. The state of the art in 2012 was 32-bit in training and 16-bit in inference. In 2021, IBM unveiled their first chip that was able to incorporate ultra-low precision, and they showed that they were able to do training in 4-bit and inference in 2-bit. So what we can see here is that by lowering the precision, you can cut training time and also the cost for training your models. And there is a lot of innovations in hardware that can help speed up scientific computations. And I think as statisticians, we should take advantage of these innovations and exploit the kind of performance that they offer. There are many low precision floating point formats nowadays, not just half and single. We have Google's Brain floating point format, 16-bit. It's more lightweight than single precision, but more accurate than half precision. You also have NVIDIA's TensorFlow 32, which is lightweight than single precision, but more accurate than half precision. So the trend is that whoever makes the hardware also makes their own floating point format to optimize the performance. The world of precision can be categorized into two, the full precisions and the low precisions. Full precisions are those that are very, very accurate, but they take up much more memory. And they are ideal for precision demanding tasks like combinatorics, number theory, and cryptography. The low precision formats are those that consume smaller memory with lower accuracy. And they are preferred in scenarios where computational speed is very, very crucial and slight loss in accuracy is acceptable. If you do low precision, you obviously can enjoy jaw-dropping speed, but there's definitely some speed accuracy trade-off. The advantage of using low precision is that you can fit more numbers, you can store more numbers, you can transmit more numbers. You can compute faster, use less energy, but the disadvantages are there. You need specialized hardware to do those computations. You limit the numbers that you can represent. You introduce quantization error. That is when you store a full precision number in a low precision format. And you obviously will run into rounding errors and unstable numerical results. And you might have to develop a completely new algorithm to make the whole low precision implementation work. To illustrate what we mean with problems with low precision, we have this table, the consequences of finite storage. So we are using this double. Without question, we use that. The machine epsilon, the rounding error is very, very small. So we are able to approximate real numbers very, very accurately. 2.2 times 10 to the power of negative 16, that's very, very small. The lowest possible value that you can store is very, very small, which is good. It does not round down to zero. The highest possible value is very, very large, which is nice. It does not round up to infinity. If you go down to single precision, the rounding error is much bigger than the double. It's now 1.2 times 10 to the power of negative 7. The lowest possible value is higher, and the highest possible value is lower. If you go down to half precision, the rounding error is very large. It's about 0.0001. The lowest possible value is very, very large. The highest possible value is very, very small, 65,000. So if you go above that, then you will have to round up to infinity. So it's easier to overflow, easier to underflow. Those are some of the problems with low precision. To illustrate what happens with your computations if you are not aware of this problem, then this is a typical Monte Carlo simulation of call option prices. So you simulate several steps, the possible call option price trajectory. The double is the standard. It's in the solid line. As you can see, the three of them start maybe at the same trajectory, but after a few iterations, the half precision, this one in the bottom, completely diverges and goes to a different solution. Another example would be this physics. I think this is a PDE or ODE. The correct result is in the third column. The double precision will give you these values in the second column, and you're accurate up to the 50th iteration, and for the single precision, you will completely go to a different solution after the 20th iteration. But there is a solution. We cannot just give up on low precision. We have this multi and mixed precision computing, and it solves the problem of loss of accuracy introduced by completely going low precision for all your computations. So the solution is to determine where extra precision is needed and where it is not. And this is what we do in multi and mixed precision computing, where we use various floating point representations to accelerate computational tasks without sacrificing the accuracy of the results. Multi and mixed, they sound very similar. Multi-precision is actually different from mixed. You have to use different floating point formats at different portions of your application or algorithm. So first line of your algorithm will use precision 1, next line will use single precision, next line will use half precision. Mixed precision, you use different floating point formats in one single operation. So this is what multi-precision computing looks like. This is the iterative refinement algorithm to solve AX equals B. This is what is going on under the hood when you compute AX equals B in your computer. The traditional version is doing everything in double precision. To do multi-precision, you can switch to different precisions for each of these lines. So first, do your LU factorization with half precision, FP16. Then you initialize, you store it as half precision. Then you compute the residual and store it and be more accurate. You use a double precision representation. Then you solve in line 5. You can use a precision US, which is either the U or the the half precision UF. So this whole algorithm is going to be much faster than the traditional iterative refinement with all double precision, but it's much more numerically stable and accurate than doing everything with half precision. Another version of that algorithm, this time with 5 precisions. This is what it looks like. So you can propose your own algorithm and give some conditions on the type of precisions that the users can choose. Now for the mixed precision, it will look like this. You can add a half precision matrix A, a half precision matrix B, multiply them, then add either a half precision matrix or a single precision matrix. Then you store the result as either a half precision matrix or a single precision matrix. This is from NVIDIA's keynote. Whenever they unveil a new hardware, they usually give this presentation and suggest how to do computations with their new GPUs. If you do a lot of multiplication, then sum, this is also a suggestion on how to do that. It's gonna be much faster than everything in double precision, and it's more accurate than doing everything in half precision. To do machine learning training, this is how they suggested one can do mixed precision training. You save your weights as half precision, do forward pass, then save the loss as single precision, and the gradients can be in half precision and some of the other gradients in single precision. So you switch back and forth. The goal is to get accurate results, but still becoming faster than the traditional double precision. Cholesky factorization has a mixed precision version where you have single precision lines and also half precision lines. You can read more about how to do this mixed precision Cholesky in these papers. Another proposal for a mixed precision Cholesky is here. So in the remaining time of my presentation, I want to discuss this MPCR package. It stands for Multi and Mixed Precision Computational Statistics in R. It's available for you to download right now, and you can try doing double precision MPCR, single precision MPCR, and half precision MPCR. It provides our users with multi and mixed precision data structures and computations. So the results that you see in the first few slides of this presentation, you're able to enjoy that kind of speed when you use this package. It has the half precision, single precision, and double precision. This is the package software stack. So you call it in the R environment. And the RCPP package links the C++ environment underneath that powers all those really, really fast computations. To install the package is very easy. You install it just like how you install other packages. So you can try the CRAN version, install it packages MPCR, and to load it to your session library MPCR. There is also the GitHub version. You can go to our GitHub ststs/mpcr and also download it from this site. To create MPCR objects, it's very, very easy. You can instantiate new MPCR if you want a zero vector with 6 elements. Then you specify the precision. It's very easy. Double precision, put double, single precision, put single, and for half precision, put half. You have to also be aware that you need to check your computer if it supports half. If you put half and your laptop does not have hardware that supports half precision, it will automatically do the single precision. Then you can print values from the vector, from this object, and you can do all the different kinds of linear algebra operations to that and do transformations of matrices, transpose, and change the dimension of your matrix. You can convert between MPCR to R. So if you start with MPCR object, then to make it an R object, just MPCR.toNumeric vector and put the MPCR object inside. You can start from R and turn it into an MPCR object. So you start with the usual how you make a matrix in R and then convert it to an MPCR matrix. You can do several operations that you need. We support all kinds of operations for these computations. So addition, multiplication, all the basic stuff, operations that R provides, this package also supports. One thing you need to remember or be aware of is that the resulting MPCR object inherits the highest precision. So if you add S1 and S2, S1 is single, S2 is double, the result is going to be double. So that's just one thing that you need to remember. Now, how can you use MPCR to accelerate your workflows so that you can do your experiments faster? You can debug. If you find some mistakes, then you can run them again and don't have to wait for a long time. You can publish faster. MCMC with MPCR. So we do a lot of Metropolis Hastings algorithm to generate samples from a target distribution that may otherwise be difficult to sample from, and MPCR can help. It supports low precision computations, fast inversion of a high dimensional covariance matrix, fast vector matrix operations when evaluating the Gaussian log likelihoods. So let's say we want to generate a two-dimensional spatial Gaussian random field, and you have a 120 by 120 grid. So that's about 14,000 locations. You will have 14,000 by 14,000 matrix to deal with. That's a dimension of this problem. There's a bunch of linear algebra operations you need to do every single iteration, and MPCR can help. What you do is very simple. Just define everything in MPCR, single precision, your mean vector, your covariance matrix, and this solve is very, very fast, as you saw in my first few slides. You blink and you'll miss it. To compare the execution time, if you use R, you will have to wait for more than 1 hour. And for MPCR double and MPCR single takes just a few seconds or minutes. Qualitatively, you will get the same similar results. So this is our starting random field, and we want something that looks like this. For R double, you need to wait for almost 3 hours. So you can drive from Yukon to New York, and it might still be running. If you use MPCR double, 42 minutes, MPCR single, 19 minutes. So just go to Starbucks. When you come back to your office, it's done. MLE, we do a lot of MLE. And there is this notorious thing, inverse and log determinant, that is a source of frustration if you have a very large problem. Same thing. We have MPCR tile here, which is another way you can store your matrices and vectors and use our other linear algebra functions to solve your MLE problem. Qualitatively, the results are very, very similar. I'm sure you will agree with me. You've seen yourself do this. 2 days to wait until you get your solution. MPCR double, 3.6 hours. MPCR mix, you can do different strategies to use MPCR, 2.3 hours. And the parameter estimates are not that far from each other. And you will get almost similar negative log likelihoods. PCA is also notorious for some computational bottlenecks. You have to compute SVDs of very dense space-time data. If your T is large or N is large, then you will take some time to compute. You can try the R version. It's going to be very, very slow. And you can compare it to MPCR version, which is much, much faster. R double, you have to wait for 1 hour. MPCR double, 5 minutes. MPCR single, 3 minutes. That's a huge difference. And qualitatively, the maps look the same, just a difference by a few decimals. And the percent of explained variance are very, very similar. Another application would be INLA. INLA, it's also a popular framework in Bayesian inference. There is this INLA package. Another one, they have INLA Plus, which is for non-sparse models, and they're very, very fast. We tried this MPCR in the INLA method to accelerate some of the computations using low precision approach, and we got some interesting results. We also get the same solutions with R double, which is the baseline or the benchmark. and much more of faster execution time with your INLA problem. So to conclude, the message for this presentation is that I think we should ride the wave of hardware innovations. Computers are getting faster, and the statistical community can exploit those new developments. Low precision arithmetic can make larger problems feasible and faster. Mixed precision solves the problem of having less accurate solutions with going completely full low precision. But so it keeps accuracy where it matters and saves time where it doesn't. The MPCR package brings these advances into R with familiar syntax and data structures. There's a lot of opportunity for designing new algorithms that take advantage with the advances in hardware to unlock performance. The future is going to be faster workflows. Your very complicated stat models, if you're able to make them, to fit them in a faster way so that people can explore and use them, then that would really, really help the whole community. So these are the references. If you want to, there is the CRAN documentation for MPCR. We also have this archive documentation, and these are some of the related literature for this talk. So if you have any questions, I'm not sure if we have a chat, and you can just email me. And also, yeah, go Jordan.
Yeah, thank you very much, Mary, for that fantastic talk to kick off this seminar series. I think it is possible to do, obviously people can't clap because they can't turn the mics on, but there is a clap reaction if I press, which I don't know what happens if anybody else presses it. So yeah, just if anybody wants to ask any questions, you can do so by typing in the chat. We do have some questions in there already. And the first, Mary, if you can sort of go back to, and I felt like you sort of skipped over this a little bit. Slide 49, you talk a bit about integration with the package and inler.
Yes.
Or maybe a bit. Is this a standalone package that you're proposing here? Or will this be integrated within actual sort of standard R inler?
Yeah, so what we did here is that write an inline method from scratch and just define all those vectors and matrices in half precision. If you're interested, you can collaborate with us so that we can just insert the functionalities of MPCR with your packages. But right now, as long as you define your computations in vectors and matrices, this R package, use them to define your vectors and matrices, then do the Cholesky, all those linear algebra operations. So that's what the package does. But yeah, we're open to inserting this into any other packages.
Yeah, fantastic. Who came up with the acronym Inshallah? Because that's gold, right? I mean, that's absolutely fantastic.
Yes, so that came from my collaborators, because this was a project done in the Middle East at KAUST. So if you know KAUST, we like to say Inshallah. So, and it fits well with INLA.
I think you answered one of the other questions we got in the chat about sort of can you combine package with, for example, SpatStat, but I guess you can't do that per standard. Whoever is the developer for the SpatStat package will have to get in touch with you to sort of implement some of these things in there, right?
Yes, so what I would say right now, if you can define the methods you do in SpatStat in manual first line, second line, third line, and define everything in MPCR objects, then that's what you can do with MPCR right now. But if SpatStat wants to put an MPCR precisions inside the packages, then they can collaborate with us.
Fantastic. So another question then, when converting from MPCR to R, does it automatically convert the R type to double regardless of the MPCR type?
Yes.
Yeah.
Yes. That's a good
Technical
question.
question. R can get faster using OpenBLAS, OpenBLAS, or veclib in macOS. Are the presented results using the standard BLAS routines?
Yeah, Lucas, that's a very good question. So these results were using RBLAS, which is slow. OpenBLAS definitely is faster. So we'll also do that, but these were not using OpenBLAS. So OpenBLAS is faster. You're correct.
Okay. And then a question from Mara. Highlight, great talk. Just want to ask, do you have some rule of thumb that you use to know when to use a single or half precision?
Yes, that's a good question. Uh, There are some literature on how to choose precisions. We don't get into that much because if you change your precision, you might not get a stable solution. If you run the computation again, you will get a different solution. So that is also something that you need to think about which part of your algorithm is going to do single or half. But yeah, I don't have a rule of thumb right now. Depends on the problem that you have or application. And I think what you can do is to do things in double first, because that's the benchmark, and see if the solution is close to that. But yeah, no, it's still a progressing field, how to choose precisions.
I guess there are some rules of thumb from the literature though, right? Because you
Mm-hmm.
showed some examples of algorithms that have this mixed precision computation in them. So there are some,
Yes.
and I guess these rules have come up from, I don't know, theoretical study or extensive experimentation. But do you think it'd be possible to like, so for me, I use R because I know nothing about precision computations whatsoever. Um,
Mm-hmm.
and I would always be worried about making a mistake. So do you think there's an opportunity to sort of put fail safes in the package? You know, if I'm adding two things together that I shouldn't be doing or multiplying them and they've got ridiculous precisions, that the package should flash up and say, look, no, you should be doing this instead.
Yeah, it doesn't do that at the moment, but yeah, you need to double check, because sometimes it terminates before it gets to a realistic solution. So yeah.
Okay. And another question from the chat then, how does your package interact with other packages that use C and C++ under the hood, for example, Nimble?
In my experience of using this, it does not there's no conflict, I think, because the way we use it is really to define or to store those really large matrices and vectors. But I think what you're asking is, can your function from Nimble or other packages take in MPCR objects? The answer is no, it will not recognize the type. So right now you have to do full MPCR objects. So Cholesky in MPCR will work with an MPCR matrix. And if you put functions like in Spatstat or Nimble with an MPCR object, it will not recognize the object. So yeah, it still does not
Mm.
blend with those packages.
Okay. Um,
Yeah,
so we don't have any more questions in the chat, but I mean, I can keep going forever. Does this,
do you have a question?
do you have integrated GPU support?
Yes, there's a version coming out with that. So right now, this is for the CPU. Actually, the tile, we have this. I'm not sure. I did not. This one, this is for just if you have multi-core in your computer, you can also do parallel processing of your Cholesky. But there is going to be a version with the GPU support.
Do you have any questions, Jan?
You have any
Yeah, I have
questions?
one. Yeah. So assume I have a big covariance matrix then can I use this MPCR to set some part of the covariance matrix to be a full precision and some part to be a single precision?
Yeah, so this is an example of what you're talking about, this one. So you can
Yeah.
define the diagonal in double, which is in spatial
Okay.
statistics makes
Yeah.
sense.
Yeah.
Yeah. There's another
Thank you.
question from Lucas.
Yeah.
Is there a C header shipped with a package to use with RCP and OS? Can I use the MPC or did? That's a good question, Lucas. I have to check. I haven't done anything with a C++ call, but yeah, I will check.
Maybe I can ask one final question if there's no other questions in the chat. So, I mean, the results you showed are fantastic, and you get these massive speed ups.
Are you going to use this?
I probably will, yeah. I mean, I've installed it
Okay,
while you've
that's
been
good.
talking. I can see quite a few places in my codes where I could speed things up with this. What's next, right? Where do you go from here? What's the next big thing on the horizon?
Oh, well, the goal is really to integrate this to other software. I mean, to our other R package like Inla, if they want, and other spatial statistics packages out there, because we do a lot of big computations in spatial. So yeah, wider, just like single precision, wider reach and more people using it, because you're paying a lot for your new computers and the power is there. You need to take advantage of them.
Yeah, I mean, I'd love to see this in Inla, absolutely, and particularly in sort of Inla Brew as well for the actual spatial and point process modeling side of things. Yeah,
Yeah, I
fantastic first
think,
talk.
yes. So we'll see you next month. We'll send out the announcement for the next talk. Thank you for joining us. I hope you learned something. So yes, bye.
Thank you very much again,
Bye-bye.
Mary, for the talk.
Bye.